One of the most remarkable news stories in 1998 was in Major League Baseball. Two players broke Roger Maris's long-standing home run record. When the season was over, Mark McGwire had set a new standard of 70 home runs, and Sammy Sosa was close behind at 66. Several programs ago, we used descriptive statistics to analyze the distribution of baseball salaries. Now we return to baseball with well-developed methods of statistical inference in an attempt to understand the rising importance of sluggers in the major leagues. Baseball fans love to analyze the statistics of their game, and very detailed statistics are kept about baseball. Nearly every sports fan has theories about which players are the most valuable to their teams. Some say it's the power hitters. It is a little unusual for a team to come from behind in the last inning, but the possibility of such a dramatic victory is one of the things that baseball fans love to see and talk about. One way turnarounds can happen is with a homer. So power hitters are valuable to their teams because they can deliver exciting wins. On the other hand, swinging for the fence is dangerous because it increases the chance of striking out. Maybe power hitting is also a liability? Perhaps the truly valuable players are the talented fielders. They can end a ninth-inning rally with a double play or a spectacular catch. In this program, we use statistical methods to test theories about the true nature of the most valuable player, the MVP. Of course, the MVP distinction is a matter of judgment and is decided officially by a vote of sports reporters. In 1998, the official distinction went to Sammy Sosa. The title is one way to measure value, but to listen to the sports news, you might think that winning the World Series is a better way. By this measure, both McGwire and Sosa came up short. That distinction went to the players of the New York Yankees.
Number 24. They are the world champions of baseball in 1998.
We could also look at the players' salaries. It may be the prospect of a high salary that drives players to swing for the fence at every chance. Home runs are certainly a crowd pleaser, but do they win games? The managers and owners of baseball teams know that winning is profitable, so they offer the highest salaries to players they believe will increase the chance of winning. Wouldn't a player who batted in a large number of runs by hitting singles be more valuable than one who brought in fewer runs but hit more home runs while often striking out? For example, Tony Gwynn of the San Diego Padres batted in 119 runs in 1997 but hit only 17 home runs, while Mark McGwire hit 34 home runs but batted in only 81 runs. The following year's salary for McGwire was $8.3 million, while Gwynn got only $4 million. Since a winning record brings spectators to the ballpark, shouldn't defensive ability be just as valuable as hitting? There are many aspects of stardom: hitting, fielding, base running, even sacrifice bunts.
Martinez with the flip to first, safe.
In this program, we will use statistical methods to sort out the important ones from the less important. We begin with an analysis of the descriptive statistics that we computed in the earlier program. We examine the suspicions that we have about baseball with a significance test, and then we reinterpret these ideas on a regression model. Finally, we turn to multiple regression to distinguish between the various parts of baseball stardom, although we will encounter limits in this approach. It is important to understand both the strengths and limitations of statistics. A strength is the ability to go beyond isolated examples about single players or teams. A limitation is that uncertainty may be so pervasive in the observed world that we are unable to disentangle multiple causes. Our inference methods can be led astray by correlations that do not reflect causation. Here is the box plot that we made of baseball salaries to compare the various positions. When we computed these figures before, we were concentrating on ways of describing distributions. As you can see, salary distributions are skewed toward the bottom at all positions, with a few stars making high salaries. We now turn our attention away from the mere description of distributions and toward the testing of theories of statistical association. Hypothesis testing is one method we use. Regression analysis is another. In fact, we can apply both methods at once. Turning our attention back to descriptive measures, here is the median and mean salary for each position. We have deleted pitchers from the list because their value is so different from other players. The presence of stars accounts for the large difference between these two measures of the distribution center. They cause the salary distribution to be skewed. For example, the median salary of catchers was $665,000 in 1998, while the mean was much larger at $1.3 million. You may remember that the mean and the median are both measures of the center of a distribution. For skewed distributions, the gap between the mean and the median is a measure of the degree of skew. The distribution of salaries for first basemen has a much higher center. The first base median was $2.3 million, with a mean of $3 million. The only position with salaries comparable to the first baseman is not a position at all. It is the designated hitter of the American League. Since designated hitters only bat, their salary is totally dependent on their hitting. Many aging stars continue their batting careers as designated hitters even after fielding skills have declined. This is why DH salaries are so high. Surprisingly, the distribution of designated hitter salaries is not nearly so skewed. Designated hitter is the only position for which the median is higher than the mean. This distribution still has a tall positive whisker at its top. The highest paid designated hitter in 1998 was Juan Gonzalez for the Texas Rangers, who received $7.4 million. At all positions except that of first baseman and designated hitter, the mean is at least twice the median. It looks like first basemen and designated hitters may be different from other players. First basemen don't have to be very agile on the field. They rarely need to catch ground balls, but they do need to be able to catch the throws of other infielders, and to do this effectively, it helps to be tall. Perhaps a first baseman's value lies more with his ability to hit home runs. This box plot of home run distributions by position reinforces the notion that home run potential is important. The distributions of first basemen and designated hitters appear to be above those of all other positions. From all angles, our description suggests that salaries are quite different for the different positions on the field. Let us apply the methodology of significance testing to the difference between catchers and first basemen. The question we pose is, do catchers receive significantly lower salaries than first basemen? When we use this word significantly, we are referring to the formal method of hypothesis testing at the 5% level of statistical significance. In this case, it is a comparison of two means. The null hypothesis is that the mean of the distribution of catcher salaries does not differ from the mean of the distribution of first basemen. And the alternative hypothesis is that these two means do in fact differ. Recalling our testing procedure, we construct a test statistic. Here is the formula. For large sample sizes like this one, this statistic has the normal distribution, so we use the familiar 1.96 critical value. We find that the statistic falls in the rejection region, and the associated p-value is 0.0003. Thus, we conclude that the data strongly confirm that catchers and first basemen do not receive salaries from the same distribution. That is, we reject the null hypothesis at the 5% significance level. In fact, we could have rejected it at the 0.03% level. That is the meaning of the p-value. Remember, there is nothing particularly magical about the 5% level, nor should the distinction between acceptance and rejection be seen as black versus white. Rather, the evidence in favor of a hypothesis can be strong or weak along a continuous scale. Here it is quite strong, and the probability that we have made a type 1 error is quite small. You will recall the meaning of a type 1 error as the rejection of a hypothesis when in fact it is true. To be more explicit, a type 1 error would be the conclusion that first basemen and catchers receive different pay when in fact their pay comes from the same distribution. In this case, the probability of this kind of error is quite small. We estimate that it is only about 3 chances out of 10,000, what we have called the p-value. You may already be convinced that salary differences are related to hitting, especially to home run hitting. By their very nature, catchers are defensive players. Some develop into power hitters. A good example of this is Mike Piazza, the highest paid catcher in 1998. In 1997, he had a batting average of .362 and hit 40 home runs. His was the third highest average in the National League that year. On the other hand, the highest paid player in all of baseball during 1998 was Albert Bell, an outfielder who batted .274 with 30 home runs in the previous season. So far, we have been reinforcing the theory about baseball salaries and home runs by citing particular players and their performance. Let us test the theory that salary is related to hitting with more than anecdotes. Let us see how tight the relation is between salaries and hitting for the whole population of players. This table shows the median salaries and the median home runs hit in the previous year. We look at salaries paid in 1998 in comparison to home runs hit in 1997 to enforce our hypothesis. Statisticians often visualize relations in a different way, with a scatter diagram. We first make a subset of players, those who had 100 official at-bats during 1997 and who were still playing in 1998. That's still a lot of players, 329. Here is the plotting of home runs hit against salaries. Each point represents a player. It is difficult to see much of a pattern in the scatter diagram. This is because of the large number of players with no home runs, or only a few at the bottom of the distribution. Another method for uncovering a statistical relation is the least squares regression line. When we plot the least squares line, the positive relationship is clearer. A computer should be used to simplify the calculation and plotting of regressions. I will demonstrate how you can do this in Excel. You can use this method to do your homework assignment. We find regression under the Data Analysis section of the Tools menu. In order to use it, we need to fill in a dialog box. We insert the column of numbers for the dependent variable, salary, then the column for the independent variable, home runs. The labels are added to the results table if you include them along with the numbers, but be sure to click the labels box in the regression setup box. Here are the results. The least squares intercept estimate is $389,495. We might interpret this as saying that players who hit no home runs in 1997 but were nevertheless judged good enough for the major leagues earned nearly $400,000 in 1998. The estimate of the slope of the regression line is 132,452. The interpretation of this number is that each home run hit in 1997 increased a player's 1998 salary by about $130,000. Wow, one home run is worth $130,000. But how sure are we about this apparent statistical relation? The R-squared statistic for this regression is only 0.43. We can employ a significance test again to decide whether the money-home run relation is real. Now the null hypothesis that we test is that the slope of the regression line is 0. Naturally, if we cannot reject this hypothesis, we have less confidence in our regression result. The same method is used. We construct a test statistic according to the familiar formula. Then we compare this with the critical value from the normal distribution. That's 1.96 for a two-tailed test at the 5% significance level. You can look this number up in the table for the normal distribution. The test statistic is easy to compute, although usually computer programs compute it automatically, along with the p-value for this test. These numbers are found in the Excel output. In this case, the test statistic for the slope test is 15.79, much greater than the critical value of 1.96. Moreover, the associated p-value is very close to 0. The data thus strongly support the hypothesized relation between salaries and home runs. However, obviously there is more to a successful career in professional baseball than simply hitting home runs. Otherwise, players wouldn't spend years in the minor leagues honing their all-round baseball skills. In addition, isn't there a drawback to always swinging for the fence? I have often heard baseball broadcasters say that power hitters tend to strike out more often and have lower overall batting performance. One way to examine this theory uses the correlation coefficients between home runs and strikeouts and batting averages. As you might remember, the correlation coefficient measures the degree of association, and it runs from -1, a strong inverse relation, to 0, no relation, to +1, a strong positive relation. We start with home runs and strikeouts. We find that the correlation coefficient between home runs and strikeouts is 0.71, consistent with sportscaster wisdom. That is, when a player hits more home runs, he is likely to strike out more often. The scatter diagram shows that although the relationship between these two stats is by no means an exact one, the positive association is obvious. There is truth in this particular bit of baseball wisdom. We also find the correlation between home runs and total hits. It's also positive at 0.66. Notice that the slightly lower correlation coefficient is reflected in a slightly more spread out scatter of points when we plot hits against home runs. Nevertheless, the positive correlation is apparent. Apparently, swinging for the fence does not have a detrimental impact on overall hitting. Thus, owners of baseball teams are doing well when they pay their power hitters handsomely. The regression method can be extended to include more than a single independent variable. Then we call it a multiple regression. This statistical technique is widely used in science, be it social science, behavioral science, all varieties of science. This is because scientists often want to disentangle multiple causes for a single phenomenon. When we have two causes, the regression equation can be written as shown. Now the equation describes a plane instead of a line in the coordinates y, x sub 1, x sub 2. Moreover, the coefficients describe the slopes of that plane along the two axes. We can use this to compare the various correlates of baseball salaries, and we do not need to be limited to two independent variables. If we want to include 3, 4, or more independent variables, the regression is harder to visualize because we cannot draw a diagram in more than 3 dimensions. Mathematically, we could say that the multiple regression describes a hyperplane in hyperspace, even if we cannot draw a picture. Using the multiple regression method, we could easily hypothesize that salary is dependent on home runs, runs batted in, total number of hits, and stolen bases. We do this simply by adding 3 additional columns to the X variable definition. Of course, actual salaries are not really arrived at by such a formula. They are the result of complex negotiations between players and team managers involving offers, counter-offers, and the threat of trade to another team. We offer the multiple regression equation as a simplification of this complicated process. No doubt this will not be entirely accurate. That is why the error term epsilon is added to the equation. It accounts for the shortcomings of our formula. Let's try this in Excel. As before, we do this with the data analysis option in the Tools menu. One detail that I have discovered about this program is that X variables must all be together on your spreadsheet, although the Y variable can be elsewhere. These results of this multiple regression are interesting. The R-squared statistic increases a little bit from 0.43 to 0.48. The slope estimates suggest that all 4 variables have a positive relation to salary. Yet after accounting for home runs, hits, and stolen bases, the separate effect of RBIs is not statistically significant. More precisely, we cannot reject the null hypothesis that the RBI coefficient is actually 0 at the 5% significance level. We've labeled this parameter beta sub 2 in the regression equation. Its t-statistic, 1.08, is less than the critical value of 1.96. This seems a bit surprising. After all, runs win ball games, and whoever bats those runs in is responsible for them. How can the RBI effect be 0? In fact, the same conclusion applies to hits and to stolen bases. None of these coefficients passes their significance test. We might conclude, when we account for all 4 of these variables in a salary regression, the only thing that we can be relatively certain about is the home run effect. If you are feeling just a bit confused, there is a good reason for it. Why can't we separate these 4 effects with this salary regression? An explanation can be found in the way we interpret the regression model. Is it something like a controlled experiment in which the experimenter varies the independent variables, home runs, RBIs, hits, and stolen bases randomly? Not quite. We are not experimenters here. Perhaps we might think that the manager in the dugout is inadvertently running an experiment for us. The problem with the story is that a baseball season is not exactly a laboratory experiment. In the lab, a scientist would make sure that all independent variables are also independent of each other. Let me explain by giving another example. Suppose there are 2 important variables. In a laboratory experiment, they might be temperature and pressure. Researchers would be careful that each experiment receive a randomly chosen temperature, maybe by rolling a die. Then they would do the same for a randomly chosen pressure. The result would be a controlled experiment to isolate the separate effects of temperature and pressure. If they plot the experimental combinations of these variables, they would have no particular relation. Their scatter diagram should look something like this. However, this is not the way it happens in the not-so-controlled experiment called baseball. Managers do try to control their lineup, but not in the way that an experimental scientist would. Home runs, batting averages, and RBIs are far from independent or randomly chosen. An increase in the number of home runs hit, by definition, results in an increase in RBIs. There is a fundamental relation between these two variables. Their scatter diagram looks nothing like the even scatter of temperature and pressure in our randomized lab experiment. Reconsidering the correlation coefficients for our so-called independent variables, we can see the relation. By using another of the data analysis options in Excel, we can calculate the correlation coefficients for all the x variables. We see that the correlation between home runs and runs batted in is particularly high at 0.90, an indication of the non-random nature of a baseball season. There is also a strong correlation between hits and runs batted in. It's 0.85. This creates a further difficulty for our interpretation of the regression results. The fact that Major League Baseball differs so dramatically from a random experiment may be one reason why it is so interesting to fans. However, it also imposes a limit on our ability to uncover the determinants of player salaries. We are using a regression model to summarize the behavior of teams and players as they settle on salaries. It is only a simplified theory. It includes the independent effects of 4 performance variables on a player's salary. But the non-random nature of the game and the true complexity of salary negotiations mean that we remain uncertain about the relative importance of contribution of these factors. We would be tempted to conclude from our multiple regression that each home run is worth about $78,000 as long as RBIs, hits, and stolen bases are unchanged. But by definition, these control variables are not unchanged. A home run is also at least one additional run batted in, and according to the regression results, each run batted in is worth $12,000. Furthermore, home runs are also hits by definition, and each of these is estimated to be worth about $7,000. Of course, stolen bases can never be coincident with home runs, although each steal is worth about $10,000. In a separate estimate, we find that each home run generates approximately 2.7 runs. In this case, a home run should be worth the $78,000 plus $7,000 since it's a hit, plus 2.7 times $12,000, which is about $32,000. This sums to $117,000 per home run. In our 2-variable regression, we estimated $130,000 per home run. We have come a long way in our analysis of baseball statistics. We began with descriptions of the distributions for various positions. By comparing these distributions, we deduced and refined a theory about the origins of salary differences among players. We formulated our theories as a 4-variable multiple regression model. Those variables include home runs, first and foremost, RBIs, hits, and steals. Because of the non-random relationship among these 4 performance numbers, we must be quite careful in our conclusions. Our method tells us that we cannot reject the hypothesis that the RBI, hit, and steal effect is actually 0. The data are simply not as informative about our theory as we would like. We do know that together these variables are important, but we cannot disentangle their separate effects. The only conclusion that we can make with relatively strong confidence concerns the connection between salaries and home runs, the one with which we started. Even here, considerable uncertainty remains about just how much each long ball is worth. Thank you for watching.